Problem 1, a 10-inch thick gore, 50 feet in length and 9 foot height, is placed at the rate of 4 feet per hour. So that is the R in the equation. Calculate the maximum pressure developed in the concrete form, assuming the concrete temperature, so that is T 55 degrees Fahrenheit. Determine the height to which this maximum pressure will extend, and the concrete unit weight 145 pounds per cubic feet, and the cement time is type 1 without retarders to determine the CC. So with that one, we need to know which equation we are going to use, and the 9 feet high, so that is H. So the rate is 4 feet per hour and the height is 9 feet, and this is a goal. The question is goal. So let's see 3 scenarios that we discussed in the previous lesson videos to determine the concrete pressure. The first equation apply for all columns and for goals with R less than 7 feet per hour and the height for 14 feet, less than 14 feet. Our problem will look like in that H 9 feet, so less than 14 feet. The rate of placement 4 feet per hour. So we apply the first equation. To be careful, you can go back to check the next one equation. For go with R less than 7 feet high, but the height is 14 feet. We are only 9 feet, so we will not apply that equation. For goals with rate greater than 15 feet per hour, it's not. So we will apply the first equation in here to determine the concrete pressure for problem 1. So with that one, as you can see right now, what is given, we have H equal to 9 feet, and we have the rate of placements of the concrete is 4 feet per hour. So from that one, we can apply the equation, the maximum pressure on the concrete equal to CW CC 150 plus 9,000 R over T, and that you can be able to use in your reference here. So the first scenarios. CW, what is CW in that equation? That depends on the unit weight of concrete. Our problem gives us 145, so it will be the third line item here between 140 to 150 pounds per cubic feet. So it will be 1. That's the table we apply. That is table 13.1, 1, CW1. And then the C with the chemistry coefficients apply in table 13.3 here. If the cement time, we in our problem is type 1 without retarder, so that is the first line item, CC equal to 1. Everyone see that one? So go back to our problems with the table, so we can have, and you can see CW equal 1 from table 13.1, and then we have CC equal to 1 from the table. Next time I will not write the table, you know that, use in the reference equal to 1. So we can be able to plug the equation in. Pmax equal to 1 times 150 plus 90 100 the rate of placement, times 4 feet per hour, T 55 degree. So we have 804.5 pound per square feet. And then we have to check the minimum pressure Pmax in that piece of max there have to be greater than minimum pressure 600 W and have to be less than or equal to maximum pressure WH, and that basically we assume it totally fluid WH, just like the water. So you see the go into the high, the pressure will be WH that you learn in fluid mechanics, but this one concrete it's like semi-fluid in there, so it have to be less than that, or at most it equal to WH. So from there we can check for maximum and minimum pressure. So we have a minimum pressure equal to 600 W. CW should be 600 CW. So you have 600 CW and we have 5.1, so it will be 600 times 1, it will be 600 pound per square foot. And then we have maximum pressure, and it equal to WH, assume it 100% fluid, just like water. So it will be equal to W. The problem gives us is 145, and the H is 9 feet, so you times 9, so you get that one is 1305 pound per square foot. So as you can see there, the Pmax in this case have to be in that range. The maximum pressure on the concrete have to be greater than minimum pressure, so it will be 600, and less than or equal to 1305 in actually that. So you will have the answer here. Pmax is actually 804 because that in the range, so look good, and that should be the answer. So the maximum pressure on the concrete for the gold concrete is 804.5 pound per square feet. And the question also asked, determine the height to which the maximum pressure will be stand. So the Pmax will stand. So what does that mean here? The way it works is you get the form. So let me draw the form here. The typical form. Just have it here. So you have the formwork, and this is the goal. So the concrete inside, it will be like pressure, but if it's fluid, it will be go like this, right, linearly. But for this one, it will go linearly until it reach Pmax, and then go constant with Pmax. So that is the typical, unlike the water that you learn in fluid mechanics or hydraulic and hydrology. So that one here. So to make it specific in this problem, we have the height of the goal is 9 feet. And the question is, what is the height to which the maximum pressure will stand? So that one, to how to determine that, so let's write down here for one time. To determine the height of the maximum pressure. And in this case, the maximum pressure we are talking about is Pmax. Maximum pressure Pmax. Then what do? We set what? If we call the height from the top to the first Pmax achieved is H apostrophe. Then with that we can have the because it's linear, just like fluid mechanics, we have the W, the weight of unit weight of the concrete, times the H apostrophe, it equal to Pmax. Just the first Pmax reach here, right? Pmax. And then we have everything, just H apostrophe we don't know, so we can have that is the H apostrophe equal to Pmax over W, unit weight of concrete, so Pmax equal to 804.5, not 1305. That is the maximum pressure that Pmax have to be less than or equal to that. Divide by W, 145 pound per square foot, so it will be 5.5 feet. So what does that mean? Here equal to 5.5 feet, and the extent that get Pmax from the bottom of the goal, so that is 5.5, so we have 3.5 feet for that. Makes sense? So what if you find out H apostrophe is like 10 feet? It means that more than the height of the goal, 9 feet. So it means that it's totally fluid throughout, so it's linear throughout of the height of the goal. That you will see in the next problem 2.